Hi guys, it's Hesam and we are back to talk about how does a Tesla Model 3 knows the state of the charge. So there are lots of challenges in measurement of the state of the charge in battery, and there are applications and chemistries that has different properties and affect what's going on inside a Tesla battery. So Tesla tells owners of rear-wheel drive Model 3 to charge up to 100% every week. It also tells long-range owners to stop at 80. Same car, opposite advice. That's not a battery health tip, it's a confession. The car doesn't actually know how much charge is in the battery, it's estimating. This presentation explores why the estimation goes bad and how the BMS system corrects it. As there is two different chemistries for Tesla Model 3 batteries, one for long range or performance battery and the other one for rear wheel drive, which is the standard. So the cell chemistries on long range is from nickel, cobalt, aluminum, which is a nickel base, or either it is NMC or NCM, nickel manganese cobalt, but rear wheel drive is lithium iron phosphide. And these two chemistries really have different properties. Once you take a look at the long range, it can consist of 2,170 cylindrical cells and goes to the typical voltage of 350 volts. And the capacity goes to 233-ish amp hour, which can be translated into 82 kilowatt hour. So the advice is charging up to 80% daily. Once we take a look at the other option, which is the LFP battery, it consists of prismatic cells, and the typical voltage goes to 355 volts, and the capacity can be translated as 161 amp hour, which can be said as 60 kilowatt hour. So the advice is to charge up to 100% weekly. So why this SOC matters here? First of all, the driving range prediction. The second of all, the supercharging taper control. And third of all, the last but not the least, preventing overcharging or lithium plating that can either make the copper dissolution on the over discharging side as well. So the BMS system needs a state of the charge for both chemistries because a state of the charge derives the range of the dash, the supercharging taper, and the safety limit. So these three are the most important ones. So let's talk about what is the state of the charge. The definition here is important. Physical definition says that SOC is the fraction of the cell's present usable charge compared to its full charge capacity. As you see on the screen on the left hand side, it is shown on the formula. So why SOC is not voltage, why it is not energy, why it is not representative of the absolute yardstick. So this is important. A pack reading 350 volts at rest is 30% SOC. Pulling 500 amps at 350 volts, it is 700 SOC. So it always gonna be showing another number if you've been talking about the voltage. Why it's not representative of energy? So let's talk about voltage sags. The last 10% of the SOC contains less than 10% of the total energy. So it is not representative of that. The other thing, why it is not the absolute yardstick. So Q or capacity fades with age. As you see, 100% on a 6-year-old pack holds less charge than a new one. And that's really important to talk about. The physical definition of the SOC is an integral, but once we look at the equation actually is, it's a definition, it's not an algorithm. So it assumes you already know where you started, that you know the capacity exactly, and that you measure current perfectly. So the real hardware actually fails at all these three. And that's where the estimation of the state of charge is getting more and more important. Charge cannot be measured and we need to estimate it. It's an important question that we need to answer here. There is no charge sensor inside a BMS. The BMS only receives voltage, current, and temperature, and all three can mislead. There are lots of issues like ohmic drop that causes terminal voltage changes with current. 250 kilowatt charging sags terminal voltage by 40 volts. The other thing is going to be the flat plateau. The LFP batteries open circuit voltage moves 1 millivolt per 1% state of charge. This signal is the size of the noise. The other issue might be the temperature. Once the weather is really cold, specifically in Chicago area and Midwest, internal resistance alters the voltage map. The other thing is going to be battery aging. With years of using, the battery capacity fades and resistance grows over time. Other thing is going to be sensor noise. So a tiny bias of 1 amp over 233 amp hour pack integrates to 0.43% of state of the charge error every hour. That can compound to 12% over time. So overall, we cannot just measure state of charge because nothing looks inside a cell and counts lithium. We rely on sensor, but a 250 kilowatt charge sags the voltage by 40 volts. Temperature shifts curves, cell age, and a tiny 1 milliamp offset on your current sensor will add nearly 0.5% of the error every hour. So there are lots of methods for estimation. So we are talking about all estimation. On the right hand side, you would see the way of the coulombic counting, the simplest way to track state of charge. So it starts with an integrating over the current over time. And then with that one, we can find out what is the remaining charge stored in this system. There are lots of advantages, like it is simple, it is real-time, it is cost-effective, and no complex modeling. But there are also limitations on that. It needs accurate initial SOC. You need to know where you're standing because your estimation is dependent upon that. The error accumulates over time and affects by battery aging and drift. In practice, it is really hard to make sure if that stays at a good level because your estimation is dependent upon that. The error accumulates over time and affects by battery aging and drift. In practice, it is really hard to make sure if that stays at a good level. And as you can see on the formula side, it's an open loop system to measure and estimate. So there's no way to correct for a bias. And as you see on the slide here, so the drift problem is really important because a little bit of bias of 1 amps adding up every hour can lead to a drift of 12%. Including these, we can take a look into other methods of estimation. For example, open circuit voltage. So in this method, actually, we do have more of thermodynamics mapping of the voltage. The input here is going to be cell voltage, temperature, rest period, and calibrated OCV mapping. As you see on the plots, for specific chemistries, you do have smaller range for plateau. And on the plot, you see axis shows OCV versus a state of charge. So here, the advantage is going to be we are having absolute metric, not accumulated drift history. And the other thing is going to be the only method capable of resetting an accumulated error, resetting an accumulated error is going to be this method because we do have that plateau area which gives us less amount of error to model. But there are also limitations for that. For example, it requires rest, 30 minutes to 2 hours useless while drifting. And the LFP hysteresis that you might see on the right bottom image on the inside of the plot shows that if the pack rests until the current is 0 and terminal voltage equals OCV, it inverts the map. So these are issues that might happen. But across the middle of this range, you see a plateau area that gives you lots of information about correlation between the error numbers of OCV and the state of charge of your battery. So Tesla's recommendation is 100% correct. So they are saying that for a specific model, you shouldn't go above a certain range. And that's why on the circuit model, which is going to be a more accurate model, we can take a look and see what does it mean and why it is really important to don't go over a specific value that Tesla talks about. So the battery model is going to be more accurate. We are going step by step. So in this method, as you see on the image, you do have an equivalent circuit model diagram featuring OCV, resistances, and capacitors. So the OCV is open circuit voltage that comes from thermodynamic side. Resistances are the internal resistances, ohmic resistances that happens during the charge. And the R1, C1 is going to be the kinetics and diffusions, how slow the relaxation happens. And the voltage is going to be affecting by time over time and is going to be showing the terminal voltage, the measured output of your system. And I of t is going to be the current, which is the measured input. Whatever we saw in the other method is going to be used as an extended common filter cycle in a Tesla battery. So we have the measurements, the capture, I, V, and temperature sensors that goes every 100 milliseconds. And then we do have the prediction based on the estimations that we have, the column count forwards using the current input. And then it will do a comparison against the model. That's going to be the innovation part. It will add some weights for the errors by the gain L, which is going to be based on the slope of the OCV curve versus the state of the charge that we described in previous slide. And then the correction happens. So there is uncertainty parameter happening. So all this have been implemented in a Tesla car to give you a better performance, because it is important to know that 1% of a state of charge is going to cost you 3 miles. And a small change in that is going to give you a really hard time in your car performance once you are in a trip or something and when you want to go to a supercharger. So you don't want to stay in the way and don't get to the destination at the right time. So that's the important thing to make sure. The other important thing is that this is going to be a loop, an algorithm. So you start with a process of measurement to the corrections, but it's going as a loop and an algorithm. So the early iterations of that was only a model that was predicting something, but this extended common filter is giving you another level of control, which involves a feedback to the system of the computer of the car. And it's going to be expanded as the years goes on and as the Tesla company is reevaluating this type of models with the advancement of AI and machine learning techniques. So overall, there are advantages and disadvantages to these methods, but EKT is a brilliant method. So as we talked about, BMS role is beyond the dash. We talked about charge control which was important really because we don't want to overcharge and do lithium plating or dissolution of the anode. It is important to restrict the breaking current when the state of the charge is above that 90% area to avoid this stuff. And it is important to do the cell balancing, equalizing the SOC, not only talking about the voltage. And the most important thing is the state of the health of the battery over time. We need to control it, and BMS can do that. So, and it is important for the safety buffers that prevents overcharging and discharge runaways. So that was the idea behind a Tesla Model 3. And why does Tesla say for a car with a different chemistry, you should go with different values of charging? So that was the idea behind a Tesla Model 3. And why does Tesla say for a car with a different chemistry, you should go with different values of charging? I think this was the first episode on the SOC, and we will continue adding up more and more elements. These are the references. Thank you for your attention. And the references for the plots and for the images is showing up in the next few slides. Thank you, and please comment for any question. Have a good one.